So I'm going to talk about instructional models of computing, so ways to teach computing, more hands-on ways of learning computing that I've found, and I'd like to talk about. So I think we all understand why computer science is important, is a vitally important subject. I mean, we're here at a Raspberry Pi event, and the whole Raspberry Pi Foundation was set up in order to promote the teaching of computer science, because computers are everywhere in our lives. We're using them all the time. And children currently at school, what will they be doing with computers in their adult life? Well, all of them are going to be using apps, using applications. All of us are using applications. Now, do people using applications need to know the fundamental details of computer science? Not really, but it can't help. Some people are going to be programming the apps, actually writing the apps. And for them, does it help to know about the fundamentals of computer science? It's probably not essential, but I think it can be very helpful to understand those things. I myself, I'm an electronics engineer. I write software. I haven't spent a lot of time during my career really thinking about the fundamentals of computer science, but now I am starting to do that. I do find it helpful, and hopefully it will make me better at what I do. But then there are some groups of children at school now who could be the computer architects of the future, computer architects designing better, more efficient, faster computers, and sometimes within local companies like ARM is quite local to here. There's a lot of people, computer architects working there, developing chips. Now, so modern computers are very complex, but here what the idea is, can we teach the core concepts, and how can we use simplified models to improve the teaching of those core concepts? So some history of computing. I mean, people have been thinking about computing right from the ancients, from people like Archimedes, through the Victorians, and right up to the current day. And through a lot of that period, a computer was actually a person. It was a job description. It wasn't actually a thing. But the problem with that is that people, they're expensive to employ, and they can make a lot of errors. So particularly in the Victorian period, they had lots of things that they needed to compute. Here's just a sampling that I could think of, star and planet tables, astronomy. Possibly that was to help with navigation, which was very important for trade. Tide tables is also important for navigation. But also things like company accounts, calculating logarithms, calculating square roots, calculating pi. Archimedes was already trying to do that back in the ancient Greece. Annuity tables, all these different things which people wanted to calculate and had to be done by persons making lots of errors. So people started to think about how could they automate this computing, because you can reduce the labour cost and you can reduce the errors. And the Victorians are already starting to think about that, most notably probably Charles Babbage, shown here. And I recently learned that the Raspberry Pi Foundation have adopted a mascot who is also called Babbage, so we can see why. And Babbage was probably the first computer architect thinking about designing mechanical machines to calculate things. And he was principally thinking about computing numbers, computing solutions to the sort of problems I talked about in the previous slide. He had an association with Ada Lovelace, who some people think was the first computer programmer, and she was thinking about how to program his machines, and she was possibly the first person to actually think about programming as not only computing numbers and crunching numbers, but also looking at symbols and doing something with symbols. And you might think, well, what's that all about? Why is that important? But if you go to your Google search bar, for example, any search engine bar, you're typing symbols in. You're usually typing words in. You might type an equation. You might ask it to solve some algebraic expression. You could type that in. But more often, you're actually typing words. What's the date of this next event? What's the next train time? Tell me about the Raspberry Pi or something. So you are asking a computer to compute symbols. So she was possibly the first person to think about that. And then in the mid to late 1930s, along came Alan Turing. And he really came up with the first very fundamental thoughts about computer science. So I'm going to talk about the Turing Machine. So which is basically this is it was for Alan Turing. It's something he thought up. It was a sort of a notional thought experiment concept. He was actually thinking of this as a person, because for him, in those days, a computer was really a person working things out. And he thought of this as a way to make a mathematical proof. So for him, the concept of a Turing machine was just a tool to come up with a proof of mathematical logic. But it turns out, in fact, that in developing that tool, he'd done something also really fundamental, possibly that people think of him as the first computer scientist. He'd really put computing onto a scientific footing and started and basically set the blueprint for how computers would look ever since. Now, I'm going to try and get to talking about briefly what the Turing machine is and why it's important. But there are a few bits of it that I'd like to try and understand, or try and convey. This might be difficult, but I'll try this. And if it doesn't work, it doesn't matter, because there are better ways to learn about this. But this is a part of the Turing machine is called a finite state machine, and this is basically a concept of a model for something which has these various different states, and it can transition between states based on an input, and then it can give an output. And a simple thing you might think of is like a turnstile in a subway or in an entrance to the toilets or something, where you come to the turnstile, it's in the state that it's locked. So that's the state it starts in, usually, unless you're lucky. You try and push on it, nothing happens. You have to put in a token or a coin, and it flips to another state, unlocked. And now, nothing happens until you push on the turnstile, you can go in, and it flips back to locked. It's a very simple concept. It's got these states. It's a bit like a flowchart, and it can move between them, and you can sort of write out the rules for these states. Now, finite state machines can do things which are really useful, actually, in communications and computing. For example, parity checker. This is often used in communications where you have, for example, 7 bits of an ASCII character, and you want to add a parity bit to just check there have been no errors, and you want some machine at the receiving end of this, if you're sending it over a link where there could be errors, to check that the parity is as it was when it was sent. A very simple state machine can do that sort of task. So state machines can do certain tasks, but there are other tasks they can't do. Like, say, something very simple as you typed into a Google search bar a mathematical expression and with numbers multiply plus divide, and you've put in some brackets, and it's important where those brackets sit, and you have to check, does every open bracket have a closed bracket? What's the meaning of these brackets? Something like that, a finite state machine can't actually evaluate for you. But there's take it the next step, what's called a push-down machine, where what you add is a stack to a finite state machine, and now you find that there are extra things you can compute that you couldn't before. A push-down stack is a bit like when you go into a cafeteria and there's a stack of trays. So it's a way of storing trays, and you can only take a tray off the top, or you can take a few trays off the top, each at a time, or you could put a tray onto the top. It's the only way you can store and retrieve data, and that's a push-down machine has a stack like that. That can deal with this problem of opening and closing brackets, but there are other more complicated, doesn't sound that complicated problems, but if you wanted to program a machine like that to say, do I have an equal number of these 3 symbols, 0, 1 or 2, you can't actually write a program with a push-down machine to do that. So that looks very simple, and you think, oh, we've got a long way to go to actually turn this machine into something that could be the whole Google, to do the Google search bar. But it turns out, in fact, you only need to add one more of those stacks to give it a second stack, and suddenly you get to one way of looking at a Turing machine. And suddenly, and this is the kind of amazing thing, is that just by adding that second stack, you now, in principle, have a computer that can compute anything that you can think of. Anything that you've ever done with a computer, anything that you've ever typed into a Google search bar, in theory, in principle, could be computed by the Turing machine. Now, Turing thought of it slightly differently. He didn't think of push-down stacks. He thought of some finite state machine that is able to read and write on a piece of tape and has a program to follow in terms of a finite state machine. But he was the first person to have the insight that something this simple could compute anything which could be computed, like anything that you type into your Google search bar. And this, to me, is a remarkable result, because it's a very simple computer, but as powerful as you will. If you think of power in terms of capability of what it could compute, it's as good as anything you can come up with. That's the Turing thesis, and nobody since has proved him wrong. So you can't come up with anything more powerful than that, but you can certainly come up with computers that are faster than that and easier to program. But I've explained a Turing machine, and some people still might be thinking, "Oh, that's a great explanation," but I still don't quite get it. That's fine. It's not a very simple concept. How do you really understand it? Well, you could build one. Somebody's done this. They wanted to better understand the Turing machine. So somebody has actually built one where they have a very long piece of tape, where they have a machine here which can write onto the tape symbols like 1 or 0. It can rub symbols off the tape. It has a webcam which can read the current symbol, move the tape. They put a finite state machine emulated inside that box there. You can go, and they've got a very nice web page for this. You can go online and see this video of this thing whirring, turning, writing, rubbing off, and that is a Turing machine. And so you could think of a problem that I want to solve. I could write a program in that and watch the Turing machine solve it. So that would be, if you had one of those, that would be a great way to learn about how a Turing machine really works. But if you can't build something like that, well, I've written something myself which I've put on a website called GitHub. I've written something in Python which will emulate a Turing machine, and I just did that for myself to help me understand it better. Can I write little programs which will do simple things? What it does is it's written in some Python code which you can see, and it writes out symbols on the console, and you can see what changes on the tape. Here I just tried to write a program which took a blank and then a series of ones and then the 0, and it just overwrites the first 0 with a blank. It's a really simple thing, but try programming it in a Turing machine. It does take a little bit of thinking about, but you can do it. It's a long way from Google, but it's a start. So you can program it. This sort of shows how that might be. But Alan Turing's original concept, he was actually thinking of a person writing things down, and this is the simplest way to play with a Turing machine, is to make your own. You consider that's the tape where there are symbols, you've got a pointer moving along. I can write a program which is rules about transitioning from one state to another state. If I'm here, if I'm in state 2, I read a 1, I write a 1, I move 1 to the right, stay in this state. That's the sort of way it's programmed. It's not an easy way to program it. If you're trying to program Google doing that, you're going to have a hard time. So, real computers don't look like that. Real computers have different architectures. They're no more powerful. They can do nothing more, but they can do it a lot faster, and they can be a lot easier to program. This is one. It's called the Little Man computer. This is a concept devised in about the 1960s. But now here you see an emulation. Someone called Peter Higginson has written a nice little emulator as a web page. You can go to this web page, and here you have a computer, and you can write programs on this computer. You can either write them by writing. It's like an everyday computer, von Neumann architecture, but it uses decimal arithmetic rather than binary. So you can write your program in terms of writing numbers into what there is the memory on the right. There is 100 memory locations. And then you can run your program. For example, there's an example here. I'm trying to add the numbers 15 plus 34. Step, step, step. Does it come out with the right answer? Yes. Good. You could write your own program to do whatever you want to do. And the nice thing with this is you can hit the step button and you can see the whole principles of the way this thing works, how it fetches an instruction, it decodes an instruction, it executes an instruction. And so you can write simple programs either as numbers or this language here called assembly language, which is similar, and it will convert these symbols into the numbers, which itself is a form of computing, converting symbols to numbers to write a program. Now, Peter Higginson, who wrote this, also wanted something that's a bit more like the modern-day computer, a bit more sophisticated. He and another chap called Richard Pawson came up with this concept of the ARM Lite, which is now, it's much closer. They modelled it on an ARM computer. Again, there's a website you can go to. You can put this up here. You see all that you can follow. You can write a program. For example, there's the game of life written, which evolves the game of life on the screen there, and you can step through this game or step through this program and see what's happening. You can write your own simple program, again, add a couple of numbers, whatever you want to do, and you can see step by step what's happening. If you make a mistake, the program's not doing what you think it should, you can see why. They've got a textbook they've written to go with this, with some exercises. Takes you takes you through, the program shown there is quite sophisticated, but they take you through some very simple programs to do very simple things, to learn the principles of how to program a chip like the ARM chip in its native assembly language, which is the way the early programmers in the 1940s and 1950s, they all used to program that way. That's how they programmed the big mainframe computers they had. But it is quite hard work, even so, and not everybody needs to learn how to program in assembly, although it's useful to, if you do know that. But really what we want to do is we want to program in a higher level language, higher level machines. And so what we really want is a computer language that's easier for us to understand, but it might be harder for the machine to understand. But that could be translated, but another computer program could come along and translate the high level language into the low level language that the computer understands, which is itself is a symbolic computation. So what we tend to do these days, writing, programming Turing machines or in assembly language machine code, that's hard work. We want to do it in high-level languages, and then we write software. There is software behind the scenes which will translate our high-level language to some, and that software might be called a compiler, or it might be called an interpreter. Sometimes you have a mixture of both of those things. What high-level languages might you use? Well, for education, here's one called Scratch. This is a language that was deliberately designed to teach computing. You have an environment. You can go online again there's a web page where you can get all this. This is used a lot in primary schools. Maybe a lot of people have already played with this. You have blocks of functions which you drag and drop together. They only fit together in certain ways, and you can write a program to do something that you want to do. Now that's great for education. One problem is it doesn't really scale up to big problems. So then you want an alternative language, and I would, that seems to be very popular in education is Python. It wasn't really, I don't think, explicitly designed for education, but it was designed to be a language that's easy to read and understand, which makes it very good for education. It's got various features, dynamic typing, indentation. These make it sort of simple to use and therefore good for teaching. It's multi-paradigm, which means that there's various concepts in computer science like object orientation, functional programming, various different styles of programming. Well, all of these styles, any of these styles could be used with Python. It's a language which is not specialized to any one particular style. And then a really good thing about Python is what you could say is like a full spectrum language. So not only is it good for the sort of first or second time programmer, but it is also very popular for real work in the real world. It is very big in various fields: system administration, web development, data science, machine learning. So you could learn it as your first language, and it could take you through your whole career as the language. So we talked about languages and conceptual machines, but what are the real life computers that we could also use to learn about computing? So here are two possible examples. There's the BBC microbit above and the Raspberry Pi below. That's a Raspberry Pi 4. We should be familiar with that. That's sort of like a whole PC on a single card. It can run a Linux operating system. It could do anything basically any desktop computer could do. The microbit is a bit more it's more cut down. It's more like the sort of computer you might have within your printer, for example. And you can connect microbits to Raspberry Pis. You can program them both using Python or a number of different languages. So they are also very good tools to play with to understand about computing. So to summarize, I've presented a few different computer models developed for educational purposes to illustrate the concepts of computer science. We started at the simplest one, the Turing machine. It's a simple model of a computer, but amazingly, it is as powerful as any computer that anybody since has ever dreamed up. And then we've culminated in the Python machine, if you like. You could think of it as a machine or as a language, which is a great educational computer language, but also is a full spectrum language that takes you up to anything, many real world applications that people are programming in their careers. Okay, thank you very much. That's that. And if anyone has any questions, I brief minute for any questions.
I was just thinking, can I take a picture of the slide of the on light stuff on?
Yeah. That's a great one. This textbook is free online. The student version, I think there might be a teacher version that's separate, but you can just, I've got it off PDF, off the internet. So the Game of Life is a little application that they provided. You can just copy it out of the textbook, paste it into there, and run the Game of Life. And it runs fast. It runs like 10 million instructions per second. This whole cell colony is evolving before your eyes really quite quickly.
Where did Python originate?
Well, there's a whole story for that, but it was originated by a guy called Guido van Rossum, who's a Dutch computer scientist. It was like, for him, it was like a little Christmas project. He was going home at Christmas and didn't have much to do. He was working in a computer laboratory that was developing languages, so he was a language designer. And for him, it started off as a Christmas project and it's kind of snowballed since, and it's now like within certainly the top 5, maybe the top 3 of computer languages, in the world.
Number 1, apparently it's the top.
It's the top, number 1.
Apparently.
Right. Certainly, there are very different ways of measuring what's most popular, but it's up there, definitely. Possibly, yes. I don't know about PHP, but a lot of these things do. I think the Python guy hit the sweet spot of.
How to use a project, and it shows.
Yeah, I don't really know much about it. A lot of people are very rude about it, and so there might be maybe some poor design decisions were made. The good thing about Python was that although this was a home project, he was actually a language designer, and he had worked on previous languages. So I think he has good taste about what is good in a language and what isn't. There were a few mistakes which they then fixed within the Python 2 to Python 3 transition, which was a huge upheaval, but seems to be now completed. So. Oh yeah, electronics engineer. So I work in wireless telecoms. I do a lot of programming in MATLAB, but some in Python where I can. And there's all sorts of. For me, it's basically my job is computing in practice. I'm supposed to be a radio guy, but I'm really a computing is the tool that I use all the time to try and solve radio problems. Okay, thank you. I don't know I think there's probably another slot. I don't want to take up another slot. But if there's no more questions, then thank you very much.